Before we simulate anything, let's discuss what this circuit actually does. 802.11af power over Ethernet includes multiple classes of powered device corresponding to expected power draw. A PD signals to the power sourcing equipment which class it is by drawing a specific current from the PSE during a signaling phase where the PSE sets the supply voltage to something between 14.5 and 20.5 volts. In other words, this circuit should draw between 16 and 21 milliamps when its input voltage is between 14.5 and 20.5 and should shut off otherwise. In this circuit, CR2, 3, and 4 are Zener diodes of 6.8, 11, and 22 volts. Q1A and B are signal PNPs, and Q3 is a signal NPN. CR3 starts conducting to turn on Q1A when the input becomes higher than about 12 volts, and CR4 shuts it off again via Q1B above about 23 volts. In that window when Q1A is on, CR2 maintains a roughly constant current through Q3, the value of which can be tuned with R71 to achieve our target signaling current. In the 48-volt steady state, high values for R72 and 73 ensure that the overall circuit only draws a few milliwatts. So with that circuit in mind, we'll go over to Altium and start by creating a new project. Now we'll quickly add a schematic sheet. We'll begin adding components starting with resistors from Altium's built-in libraries, which come provided with a simulation model. Now that we've got all of our resistors and they have values, we'll add the diodes. I don't have these diodes in a library of my own, but they do exist in Altium's content vault, which is actually like, if a part on Octopart has models associated with it, Altium will probably have them available. So in this case, the manufacturer part search has the 6.8 volt Zener available, so I'll just place that and then copy that 2 more times for the other 2 values and just replace those values and change all of the parameters so that they're not still associated with the 6.8. Now that we've placed the model compatible version of this component, we'll go back to the manufacturer part search, find the actual component with the right values and everything, and then add manufacturer data and whatnot to this component instead so that everything is just nice and clean and we could fabricate this if we wanted to. Basically, we just use the copy of the component we could find with a footprint and symbol available and then copied manufacturer data to copies of that component for the other 2 values. Q1 luckily also has models available in manufacturer part search, so we'll just use those as well. Q2 unfortunately doesn't, so we're going to have to try something a little bit different here. Note that you don't see any symbol icon in this list in the manufacturer part search window. In this case, Component Search Engine, aka Semaxis, aka FindChips, actually has a copy of this component with models, and by that I mean symbol and footprint available. So we're going to use that. I already downloaded this, if you noticed in my downloads folder, so I'm going to use their library loader to copy it into my schematic here. Now that we've got all of our components placed, let's just draw all the wires. It's important for SPICE that we draw a ground port here, and then we'll also go into the included libraries of simulation components that Altium comes with and find a voltage source to add here as well. And even though we're going to simulate a DC sweep of this voltage source later, we still have to give it a value now. And now I'll just go into Tools, Annotation, and make sure everything has a proper reference designator. Now, the last thing to do before we can actually simulate this circuit is to add simulation models to all of the components that aren't resistors and already have them. So we need to find simulation models for each of our diodes and also for those 2 transistors, or 3 depending on how you're counting. So what we'll do is kind of what you'd expect. We'll just go to the websites of those individual components and see if we can find SPICE models for each one, which we totally can. So we're just going to download all of them and then we'll go from there. So one thing to note now that we've got the model is that this is a sub-circuit style model. So we're going to have to rename the file that contains it to .ckt for Altium to ingest it properly. One thing to know at this point that really tripped me up the first time is that these sub-circuit models have to have that .ends statement and the last line, where these Diodes Inc. models, for whatever reason, included it on the same line as that last .model statement, which breaks Altium very badly. So watch out for that. So now that we've gathered all of our models, we need to associate them with each of the symbols in this schematic so that we can actually simulate with them. We do that by opening Properties for the symbol and click Add Simulation Model. And then in this dialog, we'll pick type SPICE subcircuit and then browse to find that model file. Oh, not browse, full path to download that file model that we downloaded earlier. Open that .ckt file. And then we just need to appropriately name the model as the same as what's ever in that .ckt file. So you'll see as soon as we get this name right, we'll be able to see when we click on the model file tab down below that the model is actually associated correctly. In this case, that name that we picked isn't actually right. So if we go open the model file, we can see, oh, it's named DI underscore that diode name. So we'll pick that, go back and rename the model name, and there's our model. Okay, so now we're prepared to simulate with this particular diode. Except for the one last step, which is to make sure that the pins in the model are associated correctly with the pins in the schematic symbol. So we'll just open up this port map tab and make sure that the anode and cathode are lined up. We can see in the model pin 1 is anode, pin 2 is cathode. So we'll go back over to the port map and make sure that that's correct per the schematic symbol, which actually maps pin 2 to 1 and 1 to 2. So of course I just went ahead and did that for the other 2 diode models as well. Now we have to associate the models for those transistors, which gets a little bit different. Mostly the process is the same. So for this single package 3-pin transistor, we just associate a sub-circuit model the exact same way that we did for the diodes. And then we'll go to the port map and make sure that the pins line up appropriately. This is a little bit confusing because this model doesn't give us a good idea of what pins are what. So it turns out that in SPICE, a general convention is BJT pins go in order collector base emitter, pin 1, 2, 3, which is actually, we see, different for this model. So the pins aren't going to map up perfectly. Where SPICE assumes collector base emitter, this package is actually numbered emitter base collector, so exact reverse order. 1, 2, 3 becomes 3, 2, 1. So we just need to align that properly in the port map. Q1 gets a little bit trickier because this is actually a 2-part component. So the question is, how do you map a 3-pin SPICE model to a 6-pin component? In Altium's case, this is actually relatively simple, kind of. You just assume that each individual part is its own standalone component. So we'll just go ahead and map that 3-pin SPICE model to the 3-pin symbol the exact same way that we did for the other transistor. What's a little bit confusing about this is not all packages behave the same way. For instance, Eagle assumes that a SPICE model has to have the same number of pins as the package component does. And in a lot of cases, this makes the most sense because like an op amp has power pins that are shared between all of the parts. So how would you map an insufficient pin count symbol to a model that has more pins? I'm not quite sure, I haven't sorted that out, but in any event, this is how you do it in this particular case. Just assume that they're separate components and everything will be happy. So we'll just go ahead and map them up exactly the same way as we did before. For good measure, when we get to the port map tab of this multi-part component, we'll see that it actually lets you map the ports. Here we go. For part 1 and part 2, I just mapped them both, collector base emitter to the SPICE model as I should do for both of those two parts, just in case I didn't want it to get too confused. But I also did it individually inside each symbol in the schematic, which is, you see me doing the second symbol here. One more gotcha that threw me off in this process. I was trying to play with Altium 365 at the same time as I was doing this work, so I tried to make these components in as like 365 managed components. It turns out the managed component system doesn't really support port mapping for SPICE models at all. So in this particular case, I couldn't get it to work properly, either by wrapping my 3-pin model in a additional subcircuit that actually expanded to the full 6 pins of the package. Regardless of what kind of gymnastics I tried to play there, it just would not let me associate a simulation model with my managed component that actually worked out of the box. So I guess if you're using managed components, just assume that simulation is going to be a pain in your butt and you're going to have to go associate models manually at the schematic level like I'm doing here. They apparently know about this and are working on it. So now we need to set up the analysis, and we'll start by adding R4 current to our active signals just to make sure that that plots by default. And we'll switch to a DC sweep analysis instead of those other two analyses. And then we'll go ahead and configure that voltage source V1 as our DC sweep voltage. And we want to target that 14 to 21 volt range. So we'll just do a sweep from 0 to 48 volts by 0.1 volt increments and expect that it will show us the change in current during that target window. Now what we're seeing here is that bug that I was talking about earlier where the Diodes Inc. models had the .ends statement not on its own independent line. If I go back and fix that, this suddenly starts working correctly and doesn't error out. Of course, now that we can successfully simulate this circuit, you'll notice that this current curve doesn't look like what we were expecting, which is an 18-ish milliamp draw during that certain voltage window. This just isn't working correctly. So what's going on here? Well, here I spent the next like 30 minutes just doing everything I could try to think of to simulate every which way, check which signals were working correctly and which ones weren't. I individually isolated each diode to see that I had them wired up correctly and verified that that was true, verified that the transistor pinning was correct based on what voltage nodes on each transistor were doing. And I finally, after doing all of that, came back around to remember my old foe last time I tried SPICE simulation, which is that capital M does not mean mega. SPICE is case agnostic, so M means milli no matter what, and a 1 mega ohm resistor has to have value 1 meg. 1 capital M doesn't mean anything. And if we fix that one thing, everything suddenly looks great. I've still got a bunch of debug signals plotted here, but if we look at that one magenta signal, it sure looks like our circuit is drawing about 16 milliamps in that 12 to 22 volt range that it's supposed to be. If we highlight that particular signal and pull out a cursor on it, we can zoom in a little bit closer. And that sure looks like the simulation says our circuit's doing what it's supposed to. Turns on a little earlier than it needs to and turns off a little later than it needs to, but that's kind of the point. So I guess in conclusion, trying to do SPICE simulation with Altium, the things to watch out for are 1. Port mapping is a little bit fiddly and takes care to make sure that you're doing it right. 2. If you're using managed components, you'll have to redo port mapping on the schematic, at least for now until Altium fixes that. 3. SPICE model errors will fail ungracefully and cause Altium crashes. And 4. Make sure your component values mean what you think they mean in SPICE.